You have come. Somebody is still on the way. I'm going to screen share mode. You can start recording.
Okay.
The previous class we have studied the basics of a bidirectional servo valve. I hope all of you are able to hear me. No feedback from the audience. Are you able to?
Yes, sir, we are able to hear you.
Are you able to hear?
Yes, sir, we are able to hear you.
Yes, sir.
Okay.
Sir.
Okay. Yeah. Any doubt with respect to the previous class, the orifice flow equation we derived, and also we made a generic equation of QVS, that is a supply flow to the actuator chamber, which is given by CdWxV by square root of rho into square root of 2 delta PV. And what we were telling is that for two different cases, we derived the servo valve flow equation. All the equations we derived based on this fundamental spool valve equation with a rectangular port orifice. And what we concluded is that Q is given by CD into W into XV, where XV is the movement of the spool land, relative motion of the spool land with respect to the port. If XV is equal to 0, no flow, and the flow is proportional to the square root of the delta P across the rectangular port. Now that can be configured into a 4-port servo valve, which 4-port spool valve, which is controlled by 3 lands. All the 3 lands are connected on a single rod. That's why it's called 3-land 4-port bidirectional. Now comes the name servo valve, a hydraulic valve which is used for servo application. Definitely servo application requires bidirectional flow, and that's why the special name is given now to that, such as spool valve. And we can assume, first let us assume that the openings are very critically adjusted. That is, the width of is exactly equal to the width of the opening here. And at xv is equal to 0, all these opening values are 0. When xv is moving, that is pushed towards the positive side, Q1 and Q3 will open from 0. And when xv is negative, that is when the spool is pushed towards the negative side, Q2 and Q4 will open from the 0 value. So we can analyze the flow case under 2 cases. One is xv greater than 0, another is xv less than 0. For xv greater than 0, the other port openings, that is R4 and R2, are infinity because they are totally closed. So we have to consider only this path. When xv is less than 0, R1 and R3 are going to infinity. So we will consider only the other part. Separately, we are able to write the flow pressure equations. Finally, 2 delta PV is equal to PS minus PR minus PL here. Whereas here, this 2 delta PV is equal to PS minus PR plus PL. Why that minus has become plus here is, we assume the same sign convention for PL under both these cases. That is, this side is assumed as positive, this side is assumed as negative, so that PL is having the polarity. plus minus. That is the reason why in the reverse condition, PL, the polarity, the sign of PL becomes. Equation can be combined in a single equation by introducing the term signum function of xv, because when x CdWxv by square root of rho, that is coming from the previous spool valve equation, multiplied by square root of 2 delta PV. 2 delta PV, one problem, say anything if you put under the square root, when that sign of that particular term becomes negative, the square root will become a complex number. So we don't want that. So what we do, we take the magnitude, put the magnitude only under the square root, then sign is taken outside. And delta PV is given by here PS minus PR. I am neglecting PR because PR is relatively very small. For example, PR will be of the say 2 delta PV, suppose the polarity becomes negative, what will happen? The direction of flow will change. Now, 2 delta PV positive means PS minus PR minus PL is positive. That is, this is at a high pressure level and here there is a drop. This drop is positive and this PL drop in this direction also is positive. And here also it is positive, so that flow will be along this direction. But if 2 delta PV is negative, here PR cannot increase. The only possibility is PL will be taking the opposite direction. PL become very large. Suppose PL is so large, it is even more than PS. Then PS minus PL will become negative. How it is possible? Suppose the load is driving back the piston. Then what will happen? Here, it has a reverse direction. Pressure drop will come and that will push the flow. There is a, instead of hydraulic actuator like acting as a motor, if it is acting like a generator and some very big force is applied on this, suppose we push it back, then this pressure will be driving the flow backwards. That is what is happening. So this term, if it is becoming negative, the meaning is flow becomes the opposite direction. So by taking the magnitude here under the square root and multiplying by the sign is physically also consistent. So there is no problem for this equation. This is the net equation of the servo valve. Any doubt on this?
Sir, when we say 4-port valve, so both the output port are counted as one, right?
Are you telling about this?
No, sir, the PR ports.
PR port. This port?
We are saying 4-port valve. So
Yeah.
PS is one valve, then the two valves to the hydraulic cylinder, and the two output PR valves are considered as a single port.
No. I will tell you. Physically, what will happen is say, even though this is, I have shown it as a big tube, this itself will be really split into two parts. So this is one, this is another port. This is one port, this is another port. That is why Q1, Q2, Q3 and Q4. These are four physical rectangular openings will be there. Now here one, here another thing, here another thing. So these are counted as two separate ports. And actually this PS, there will be a block here. This PS may be routed into two halves probably in the real construction. And this is one, this is another port. This one port, this another port. Total 4 ports.
Okay, sir.
Out is clear?
Yes, sir.
Okay. No other doubt, I hope. And this hydraulic actuator, this is a piston cylinder mechanism, as I told. Both sides piston rods are there. Even though one side rod is sufficient, now I have given other side also rod just to make the actuator symmetrical. Otherwise, forward chamber area of cross section will be larger than the return chamber's area of cross section. No problem, that way also we can configure. But for simplicity, I have shown both the volumes are equal, both the area of cross sections are also equal at null condition. Now
You were comparing this with the Wheatstone bridge in the previous class.
Can you, I am
Hello?
not able to hear.
Sir, you were comparing this with the Wheatstone bridge yesterday,
Yeah,
but you did not explain the interfaces.
okay. Say, I have explained these two parts of Wheatstone's bridge. The difference between the actual Wheatstone's bridge and this particular circuit is, in the Wheatstone's bridge, we put all the resistance together. Here, as I told, when XV is greater than 0, these two resistances are infinity. The Wheatstone's bridge only configuration point of view only it is corrected, not with respect to the balancing and all.
Okay, sir. Okay.
Balancing also we can do it, not with this particular thing. Balancing comes when there are leakage flow. These two things are not infinity. When they are not infinity, then simultaneously we have to consider all the resistance. But now I am considering ideal case where in one case these two arms are having infinite resistance, and the other case these two arms are having infinite resistance only. So half of the Wheatstone's bridge is considered. And if you really interested to analyze more realistic cases I am just coming to such cases where always all the ports will have some finite opening, then actual Wheatstone's bridge arrangement will come.
Okay.
As such, you are understood this, whatever I have written, right?
Yes, sir.
This drop only I have written, PS to PR. First part of drop is about R1, then drop is about the cylinder, then the Okay, there was a connection problem. Okay, are you able to now see the screen?
Yes, sir.
Yes, sir.
Okay. I think the last part is missed. So what I was explaining is the total drop from PS to PR is converted into drop across R1, drop across PL, and drop across P3. So we are adding. And if we assume symmetrical, exactly symmetrical flow control valve, this drop across R1 is same as drop across R3 because the flow through these both the paths are same, and also geometrically the area of cross sections for Q1 and Q3 will be same for a given displacement of this. That's
Sir,
what I am.
sir, how the drop will be happening across that PL which you have written? How is that exactly
Yeah.
happening?
That is because of the back pressure. See, you all know this is a piston cylinder arrangement, and assume that you are connecting it to some load. Assume that it is totally blocked. Just assume. If it is totally blocked, what will happen? No motion is possible. Then entire flow, there won't be, all the flow will actually get accumulated here, and this entire pressure finally, pressure PS will come here, right? You agree? Because no continuous flow can be there. Full PS will be coming here. But when there is a finite motion, what will happen? When there is a motion, there is a volumetric flow rate given by the area of cross section of the piston multiplied by the velocity of piston. That much of volumetric flow will be there because of the movement of the piston. So an inward flow because some volume is swept per second by the piston. And similarly, even though there is no physical contact here, because of the motion of the piston head, there is an effective volume decrease will be there, which is also same as AP into XA dot. And that is equivalent to, under flow balance condition, what will happen? Whatever, if there is no, we first assume that the fluid is not compressible. Under that condition, if this piston is moving at a velocity of XA dot, I call it as XA dot because XA is the actual displacement. So XA dot multiplied by the area of cross section of piston. When it is moving like that, there will be an inward flow by the same amount, AP into XA dot, and there is an outward flow also by the same amount, AP into XA dot. So what I'm telling is the flow rate through Q1 is equal to flow rate through Q3 is equal to the volume swept by the piston per second. Okay. That is a flow balance. And while this is happening, there is a drop across this, an equal drop across this, and there is a drop across piston because piston is not free to move. So whatever the PL multiplied by AP, that much of force is equal to the force of reaction exerted by the load at this point. Hope you understood.
Yes, sir.
Okay. Now I am going to introduce some non-linearities into the servo valve. Here we have considered an ideal servo valve, assuming that the fabrication is infinitely resolvable, there is high infinite resolution is possible, or fabrication tolerance can be 10 raised to minus infinity microns is possible, but never it is possible. Always there will be some fabrication tolerance will be there of the order of few microns to sometimes sub-microns depending on the fabrication manufacturing methods that we are going to use. Because of that, you can never realize a critically lapped valve. I have expanded one of the spool valve port. This is the port. Consider this can be, you can assume that this is a supply port. PS is coming, this is XV movement. See this particular delta, there is an overlap of the spool land across the port. This is the port opening, this is the land width, and land width is more than the, it is extending beyond the edge of the port by delta here and by delta here. Such a case is called an overlapped valve. If that is the case, the displacement of the spool will not be same as the opening. So I am going to give two different symbols. The actual hydraulic valve opening, that width is given by XV, whereas the physical motion of the spool valve is given by YV. So along the x-axis it is YV, along the y-axis it is written as XV. Okay, hey, it's not confused. YV is the physical displacement. Here you can see this particular characteristic. Until YV is equal to delta, we have to move YV by delta. Then only the physical opening will start. This is the actual physical opening. When YV is equal to delta, XV is equal to 0, just about to open. Similarly, if you move YV in the opposite direction, it has to move up to minus delta to have a positive opening for this path. So this characteristic, the servo valve overlap characteristics, relation between the physical movement of the spool land and the actual opening of the port, that is XV, can be related through such a curve. And the middle one is the critically lapped case, both are equal. And similarly, there can be overlap and underlap also. Here you can see the case. I have shown both critically lapped case, this critically lapped case, and whatever the red hatched thing is the underlapped case. That is, the even when YV is equal to 0, there is a finite value of XV here. So there is actually a jump sort of nonlinearity. When YV is equal to 0 itself, there is a finite XV, and why we are pushing further, that extra offset plus the linear change will be there. Similarly, when you consider the other direction, when YV is going towards minus side, it starts with a minus delta and then increases. So that's what I have written here. For critically lapped valve, XV is equal to YV. This requires sub-micron fabrication tolerance, which is not at all possible. Then for overlapped valve, XV can be written as YV minus capital delta signum function of YV. For example, when YV is positive, you will get XV is equal to YV minus delta. XV is equal to YV minus delta. And when YV is negative, here you will get XV is equal to YV plus delta. And when YV is in between, plus delta and minus delta, XV will be equal to 0. Okay, that also I have written only for greater than delta case or less than delta case, this is equal. So this will be complete when we are really modeling. You have to consider this case also when the magnitude of YV is within delta XV is equal to 0 also you have to write. Similarly, this main problem here is this introduces a dead zone nonlinearity in servo valve flow equation. You might have heard of this nonlinear dead zone. Why it is called dead zone? When YV is within plus or minus delta, output is dead. It is a zone in which there is no output. That's why it's called dead zone nonlinearity. The effect of dead zone nonlinearity in the servo valve equation is a drastic reduction of gain near null condition. And you have studied control system, the effect of gain on system dynamic characteristics. Here, what will happen is the closed loop bandwidth will come down or low amplitude. That is the issue with this, which if the closed loop bandwidth comes down, what I mean is the closed loop bandwidth of the actuator, when it comes down, it will go and interact with the autopilot dynamics. So there will be an unhealthy interaction between digital autopilot and actuator, which will lead to loss of stability for the autopilot, and it will affect the vehicle stability. So this, even though you may think it's insignificant, it is not like that. It is very, very important part of the overall system. Another is underlapped valve. Then you can put XV is equal to YV plus delta into signal function of YV. That is the equation for that. Here, dead zone. Instead of dead zone, here the problem is there is a sudden jump in the characteristics will be there. And this provides larger servo valve gain at null condition. So gain stability point of view, it is good, but it leads to energy loss due to higher null leakage and also results in fluid heating. That is, even when we are not giving any command to the actuator, there will be flow. For example, consider this case. We are giving 0 command to the actuator and hence 0 command to the spool valve, but there will be a flow from PS to PR because here there is an underlap, here there is an underlap. There is one flow path here, there is another flow path here. Unnecessarily, the pressurized fluid supply is lost. Leads to energy loss as well as heating of the fluid. That is not a good thing. So neither underlap nor overlap. Both are good, both are not good. Critically lapped is the ideal one, but you can never achieve critical lap. Then the question is which you will select. It all depends on the application. So you cannot allow any instability of the vehicle. Then you have to go for underlap only. Because exactly critical lap you can never make. Either you have to ask the manufacturer, a little bit underlap is acceptable, but you should not do any overlap. Or we are not ready to waste the energy, but little bit of oscillation, stability loss is acceptable. Then you can ask the manufacturer to keep always a positive value for the overlap, but never do underlap. Exactly keeping critical lapping is impossible for any manufacturer. Any doubts on this? Okay. Now, there is one more nonlinearity.
Sir, I didn't understand why underlap one doesn't allow oscillations.
Underlap one, say, first of all, oscillation, you understood what I mean by oscillation, how it comes. It is not simply due to servo valve straight away. The If you use overlap, there will be gain reduction. At null, you can see that instead of this gain, now the new gain characteristics is like this. In the next diagram, I am actually smoothing it out. So the slope is nothing but the gain. You can see that around null, the gain of the wall decreases. This directly reduces the gain of the forward path gain of the control system. If you path gain of control system, bandwidth of the control system, closed loop control will come down. Now, if actuator is a innermost element in the overall vehicle loop. So if the bandwidth of the actuator loop comes down, it will affect the phase margin of the autopilot loop. And the stability loss is actually happening for autopilot loop, not for the actuator loop. But in the case of underlap, the gain characteristics is like this. That is like if you smoothen it out, this will be the gain characteristics, which gives larger gain at null, not smaller gain. So there will be larger bandwidth for small signal amplitude. So there will be a larger phase margin for the autopilot, better stability. You understood?
Yes, sir.
Okay. Now I am going to introduce one more non-ideal characteristics for the servo valve. That is called radial clearance. That is this is finally the spool as well as the spool land, everything is made of metal. And if you keep the outer diameter of the spool land is equal to inner diameter of the spool, what will happen? This will get jammed, cannot move. So always we have to keep the outer diameter OD of the spool land slightly less than the ID of the spool, and that clearance with respect to radius is called radial clearance in the spool valve. That radial clearance will allow leakage across the radial path, even in the presence of an overlap. So even though there is an overlap delta there, the flow will not be zero during this condition. There will be a finite flow will be there. The previous diagram I have assumed zero flow. There is zero connectivity, but actually there is a finite connectivity is there. So instead of the ideal dead zone, this should be approximated like a smooth curve. Similarly, for the other underlap case also, we have to, because of this particular characteristics, you have to, you will not get such a sharp jump. Instead of a smooth curve you will get. So finally, we have to use either critically lapped valve or an overlapped valve having such a characteristics, or an underlapped valve having such a characteristics that can be modeled using such an equation where sigma is a constant, y is the absolute value of the moment, and you can just plot it. I have actually plotted in the course note how for different values of sigma and CR, how these characteristics look like. So this is the equation that is used to model the transfer characteristics between the physical displacement of spool and the effective displacement of the valve. Details are given in the course note. Okay. Now I am going to another part. This is the valve part. That is a sourcing part of the flow into the actuator. Now what will happen inside the actuator chamber? This is the second part of the diagram, previous diagram I have shown. We were now discussing about this part now, and coming to this particular part. Here there is a finite volume V1, another finite volume V2, and the forward chamber is having pressure P1, return chamber is having pressure P2. And here the volumes are very negligible, even though I have shown large volumes, but this will be a very small volumes, but the actuator inside volume will be much larger. Okay, that's why we are considering the compressibility dynamics inside the actuator chamber. In the servo valve equation, we assume that fluid is incompressible. That's okay to correlate the flow pressure equation, upstream, downstream. But that assumption we will not apply with respect to actuator chamber. At servo valve only will apply. Here we assume that fluid is compressible. We have to consider the compressibility of the fluid because that is not insignificant. How we can account for the compressibility? What we'll do is, as any compressibility case, we consider the modulus of elasticity. Here, it is a volumetric compression, and the stress is nothing but pressure, and strain is the incremental volume with respect to a given volume. So we have to define the modulus of elasticity in terms of the volumetric compression. That's called bulk modulus of elasticity of fluid. It's represented by beta is equal to stress by strain, where stress is delta P and strain is equal to minus delta V by V naught. That is, we are considering a finite volume of fluid V naught, that is a solid volume, and it is having a pressure P naught. Then we suddenly increase the pressure from P naught to P naught plus delta P, which will result in the volume to reduce from V naught to V naught minus delta V. So the stress applied is delta P, where the strain is equal to minus delta V by V naught. And this will be a positive quantity. Then we divide both the sides by delta T. Suppose this happens during a time of interval delta T. We can divide both numerator and denominator. Finally, we will get this equation. Beta is equal to minus P dot divided by V dot by V naught. Or you can take this V dot the other side, called rate of change of volume dV by dt is equal to V naught by beta into dP by dt. This is the equation used to model the compressibility of the fluid along with the other dynamics equation. Okay. Now we are considering the actuator chamber. V1, P1, V2, P2, and XA is nothing but the relative movement of the spool, the piston head, relative movement of the piston head with respect to actuator chamber. So V1, you can say it is equal to V naught plus AP into XA. When XA is equal to 0, piston is exactly in the middle. V1 is equal to V naught then. And the return chamber volume is V2 is equal to V naught minus AP into XA. V naught is called the half volume of the actuator cylinder. That is, total volume is 2 V naught. Here V naught, V naught. Now we are considering the load flow. This already I discussed when you asked a doubt. Load flow is equal to QL. It is QL is equal to AP into XA dot, where AP is the area of cross section of the piston. AP means this whatever area minus the area of cross section of the rod that we are subtracting, multiplied by XA dot. XA dot is the relative velocity of the piston with respect to cylinder. So we are getting volumetric flow rate due to piston velocity. That is represented by QL. Now, QVS is the total flow rate into the forward chamber. This flow is consumed by two quantities. One part is QL. But if you assume the fluid inside the forward chamber is compressible, there is one more part while the pressure in the forward chamber increases, the fluid will get compressed or it will shrink, which demand an extra inlet flow. That is the term V1 by beta E into dP1 by dt. Here we derive this equation V0 by beta dP by dt. Same equation only I have written with little modification. V0 now becomes V1 because I put the general equation, and beta is replaced by beta E. I will tell you what it is. Then dP by dt is nothing but dP1 by dt forward chain. Beta E is called effective bulk modulus. Here, when we consider the bulk modulus of fluid, we consider only fluid part, but the cylinder is also not infinitely stiff. When the pressure increases, the cylinder also will slightly expand, which will give additional compression. So what will happen is the fluid will become effectively more compressible compared to the original fluid because the cylinder walls also expands. We will feel as if the fluid is more compressible. So the effective bulk modulus, that will be less than the actual bulk modulus. So there will be larger compression will be there. And because of that, say dV by dt will be more, because in beta comes down, what will happen? Here beta is in the denominator. When it comes down, the overall thing will increase. So dV by dt will be more. Any doubt on this particular part? Okay. Now that part is over. Now one more part is servo valve dynamics. That is this particular case, we simply assume that there is some prime mover which is moving XV. There is a spool rod is pushed by some prime mover to create such a relative motion. It cannot simply happen. We have to connect a prime mover. What prime mover means? Some driver should be there. It can be either direct electric motor, or there can be a hydraulic pilot stage if the force requirement for moving the spool is large. The servo valve that we are using now, it is having a hydraulic pilot stage, and the pilot stage is called a flapper nozzle stage. And the flapper is actually moved by an electric motor, a small force motor sort of thing. And finally, you can express the relation between the physical displacement and the motor current by a second order dynamics. So wherever there is an electric motor and it is pushing some inertia, a second order dynamics will come. And that is also configured in a passive closed loop form. I'm not discussing the details of that because that is a bit more involved. It will be available in various textbooks. That is a two-stage servo valve with pilot flapper nozzle stage that is available. If interested students can read it. Finally, you can express dynamics of the servo valve as YV by IV is equal to KV to omega V square divided by S square plus 2 zeta V omega Vs plus omega V square. Here omega V is called the bandwidth. It will be a very high bandwidth of the order of 150 hertz and all. Zeta V is called the damping factor. KV is the sensitivity of the servo valve with respect to spool displacement. These values are available for any standard servo. Any doubt?
Sir, what is the meaning of flapper nozzle type?
Flapper nozzle actually, if I was teaching you on a board, I could have drawn it. Flapper nozzle is, I will talk only, I don't have any figure to show you. It is two nozzles will be there in between there is a flapper will be there. So in the what will happen, and the two nozzles are connected to some pressurized fluid supply. If the flapper is closing the nozzle tip, it will generate a back pressure inside that particular nozzle block. And that back pressure will drive the spool valve. So depending on the distance between the flapper and the nozzle, the back pressure inside the nozzle will vary. Here it uses the principle that the nozzle diameter will be very, very small. So if you just for closing the nozzle by a flapper, we require only small, because the area of cross section multiplied by the pressure, the force will be less. There is a concept here. If you are very much interested, I can bring I can show the diagrams and all. Otherwise, it is available in various textbooks. You can just read it if you want. For the knowledge, I can explain in the next class. Because without figure, I cannot explain. Okay. I will give a small interval. I hope some 5 minutes, because I don't want to take continuously class for you. You will be tired. So we'll start at 4 o'clock. Now it is 3:55. Okay. ഞാനൊരു കമ്പ്യൂട്ടറോടെ ഓക്കെ, കുഴപ്പമില്ല. എത്ര മണി വരെ കാണും നിങ്ങളുടെ? ഓക്കെ ഓക്കെ, നോ പ്രോബ്ലം. Okay. Okay, shall we start? All of you are there?
Yes, sir.
Yes, sir.
Okay. Now I am going to use that compressibility equation and doing some simplification of the flow equation. The basic, the reason for, or the how can I do the simplification is assuming two cases. One is symmetricity of the entire hydraulic system. Another is assume that we are moving only small amount with respect to the null condition. That is, if you consider this equation, this system, we assume that this Q1, Q4, Q3 all are all symmetric. That is, if you move, the openings will be equal, and also this diameter, everything is equal. And finally, we assume that the actuator's piston is at the middle condition, and we move only by small amount, so that we can make some approximations for the equations to get a simpler dynamics. That is, we assume that V1 is equal to V2 is equal to half volume. There is a perturbation change with respect to the null condition is small, so that we can always assume that this assumption we can make. Another assumption is dP1 by dt, we assume that equal to minus dP2 by dt. How that can be justified? Consider this case. Assume that P1 is equal to P2 in the null condition. Everything is, no load was there. So P1 is equal to P2, exactly middle case, suppose it is equilibrium condition. Suddenly, if you move the piston rightward, what will happen? If you are driving from the load side, you know that P2 will increase and P1 will decrease. Similarly, if the pressurized fluid supply is driving, so internally drive comes, then P1 will increase and P2 will decrease. The amount by which P1 increase and the amount by which P2 decrease will be equal and opposite. The delta change will be equal and opposite because we assume a symmetric condition. This is the explanation for that. Thus, we assume that P1 dot is the change in P1 is equal to minus of the change in P2. So their derivatives are equated like this. Then PL is equal to P1 minus P2. That is always valid. But if you use this particular assumption, dPL by dt is equal to dP1 by T minus dP2 by dt. This is also correct. But here, using this relationship, you can say that PL dot is equal to either 2P1 dot or is equal to minus 2P2 dot. And this equation is made, use here QVS is equal to QL plus V naught by beta E PL dot by 2. This is nothing but the previous equation we made. QVS is equal to QL plus V1 by beta E P1 dot. Here what we do is it is equal to QL plus V naught by beta E into, instead of dP1 by dt, what we did is PL dot by 2. Similarly, QVR is QL minus V naught by beta E into dP2 by dt. It is nothing but minus PL dot by 2. So these equations you will get like this. Now you can see that both are one and the same. Thus QVS is equal to QVR is equal to QL plus V naught by 2 beta E into PL dot. So let us say it is equal to QV because S and R, there is no point of doing that. This is the simplification we. So finally, the flow balance equation, that is, the flow supplied by the servo valve should be equal to the flow consumed in the actuator chamber. This is the supplied flow. Here I use two notation: Kf into N nonlinearity of YV into square root of PS minus gamma PL sine PS minus gamma PL. What I have done is this Kfn is nothing but CdW by square root of rho, and N of YV, that is nothing but the nonlinearity effect of overlap, underlap, radial clearance, all are lumped there together as N of YV. This is the supply side. Now the consumption side, load flow plus compressibility flow. So what I have done is, with respect to this system, here we are connecting servo valve. Servo valve is actually interfacing the supply of the fluid to the load. So one part of the flow is whatever is generated flow, and the other part of the flow is what is consumed. So generated flow is equal to consumed flow. Generated flow is due to the servo valve equation, what we derived, and the consumed flow is due to the load flow plus the internal compressibility. So this completes the flow path, hydraulic flow path. Any doubts on this? Okay. Now we are going to the first part of the hydraulic actuator called load dynamics and effect of structural stiffness. That is what I have shown here, the second part of that main whatever diagram I have shown. This part alone we are now concentrating. The actuator chamber, area of cross section of the piston, P1, P1, P2, P2, PL is plus minus, and XA is the relative moment of this piston head with respect to cylinder, and piston rod is connected to the load. Here I am considering a aircraft control surface like elevon or rudder. It is this hinge point or gimbal point, and the moment of inertia of the control surface with respect to gimbal point is JCS. CS stand for control surface. Similarly, BCS is the viscous damping coefficient, and the momentum of the piston rod with respect to the gimbal point is LM, and the forward displacement of the control surface, if you take it as linear displacement at the connection point, is XS, which leads to a oscillation, deflection of the control surface with respect to gimbal point. And this relation delta CS is equal to XCS divided by LM. And the force acting on the control surface, there are two components. One is due to the actuator force F of small a, another is in external disturbance force. Just 1 minute. Yes, Sajin. ഞാൻ ഒരു ക്ലാസ് എടുക്കുകയാണ്. ഞാനൊരു 45 ഓക്കെ ഷുവർ ഓക്കെ. And is one very important thing that you should remember is, see here, there is an internal force developed in the actuator. Area of cross section multiplied by the pressure drop. But this cylinder has to be fixed to a structure, otherwise its reaction path is not complete. For example, if you simply put this actuator cylinder on a tabletop and connecting this rod to a control surface, if you are trying to push, what will happen? this actuator will slide over the tabletop. It should be rigidly attached to the tabletop. Then only a forward force, FA, it can be given, because there should be a reaction path is very important. Now the reaction force is now felt on the cylinder. That should be finally applied to a fixed structure. That's what I have shown here. And the connection of the cylinder to the structure is through a structural member. Definitely it will have a finite stiffness that is represented by KL. Actually, KL represents the stiffness of the forward transmission path structural stiffness and the return path structural stiffness. If you represent this by KL, KL2, KL will be is equal to KL1, KL2 by KL1 plus KL2, the series combination of springs. So this, we can write the equation like this. Total force generated by hydraulic actuator is F suffix capital A equals AP into PL. AP is the area cross section, PL is. Now, internal loss due to viscous damping and Coulomb friction. While this piston head is moving inside the cylinder, there is a fluid film will be there. And that fluid film will give a viscous damping force due to the laminar sort of effect. Another is there will be a metal to metal contact, or even some O-rings, etc. will be there, which will lead to some sort of Coulomb friction. So total BA into XI dot into F, some constant signum function of XI dot, both together will be there. That's what I have written here. So the final force coming out of the actuator is equal to FA, F small a is equal to F capital, F of suffix capital A, that is AP into X, EPL minus the viscous damping force minus the internal friction force.
Sir, what is FD? Sir, FD,
Yeah.
what is FD? The torque equation.
What is
FD, sir, FD.
FD? Okay, FD is an external disturbance. You assume a condition, your aircraft is flying. You can see during landing and all, large aerodynamic force is acting on the control surface. So there are two forces. One is the external aerodynamic forces. Another is the force given by the actuator. Both forces together will be acting on the control surface.
Okay.
Okay. So in order to get the formula for FD, you have to find out the aerodynamic coefficients of this control surface corresponding to the angle of attack and Mach number. All such equations you have to derive. Here I am simply assuming that there is an FD. So this is the total force, FA plus FD into momentum. That is the torque acting about the gimbal point. And that is equated to the load dynamics. There is JCS into S square plus BCS into S into delta CS, where this S is nothing but the Laplace operator, you know, transform is equivalent to differentiation, 1 multiplication by S. So this is nothing but JCS into delta CS double dot plus BCS into delta CS dot. That is equal to the applied torque. Now, the reverse motion of actuator, while this is we are doing, a forward force act on the control surface, an equal and opposite force will go from the actuator cylinder to its mounting structure. So the same FA I have written, here also FA, here also FA. That FA will act across the KL, that will produce a finite backward motion. X B, B for bracket, basically FA by KL. So finally, there is a reverse motion of the cylinder and there is a forward motion of the piston. So the relative motion of the piston with respect to cylinder is equal to the forward motion XCS plus XB, where when I say plus, XCS is positive in the forward direction and XB is numerically positive in the reverse direction. So when we add plus means both positive quantities will be added to give you a bigger positive number. That is the relative motion of the piston head with respect to cylinder X of capital. That is this equation. Hope you understood. Any doubt?
Here the capital F, FA and FD both
You
are
have to be
Laplace
louder, please.
transforms,
I am not able to
like,
hear.
Sir, the FA and FD both are Laplace transforms.
Yeah, say FA,
Because
FD,
on the right side we have
equation, all will be Laplace transform of the signal. The signals will be represented in the Laplace domain, frequency. So FA you consider as a signal or FA of S, FD also a signal, FD of S, like that only. And delta CS, it is a Laplace transform of the deflection. Okay, this is now another part. So far we are discussing about the total nonlinear model. But when we start any analysis, we start with the linear system model, do some transfer function analysis, and validate our linear model. Then only we will introduce nonlinearities and analyze for the nonlinear effect. Here one problem, unlike our electromechanical actuator, where if you simply remove the friction, saturation, you can remove all nonlinearities. Stroke limit, integrator limits, Coulomb friction, yes, zero. But here that is not the case. Here the main control element is servo valve, and it is having a square root nonlinearity. I am representing again here for the simplicity I take only critically lapped valve. So KFN into the N of capital N of YV I removed. Assume that critical lapping means YV is equal to XV. KFN into XV in the square root of PS minus gamma P. Here, you see that there is a square root nonlinearity. So you cannot simply approximate by linear equation. So there requires a linearization through partial derivative. Therefore, we have to assume the Taylor series approximation around some operating point. So we assume certain operating point, say XV0, PL0, that is the valve is open around a value PL0 and the load, external load demands a PL0. For example, aircraft is flying in trim condition, and you may have trim condition, steady leveled flight. Then what will happen is the angle of the deflection, all the angles will be same, and aerodynamic load will be constant, and hence the load pressure will be constant, say PL0, but around that a small deflection, overriding oscillation will be required for the control surface to ensure leveled flight. That leads to some finite value of XV0. Actually, XV0 will be a XV will be a sinusoidal motion, but we assume that it's a constant value just for analysis point of view. So XV is some steady opening and a steady pressure, because here the parameters are variables are XV servo valve opening and PL. All other things are constant. So if we are linearizing, we have to linearize with respect to both XV and with respect to PL. Definitely you have to assume certain operating condition, operating point. That's why I given XV0 and PL0. How we will do that? We are finding the partial derivative of QV with respect to XV for a particular, here actually I have to put a line at a particular operating point, which can be obtained like this if you differentiate with the XV. This straight away is proportional. So KFN into square root of Vs minus VL0. Here I assume XV0 is greater than 0 and Ps minus VL0 greater than 0. So the magnitude part is removed. Similarly, Kc is equal to minus delta QV by delta PL, differentiating with respect to PL, and we get this equation XV0 PL0. Thus we get, why I put my explicit negative sign is, the reason is if you find the numerical value, otherwise it will be negative. In order to make that only, to make it positive only, because as we increase the value of PL, what will happen? There will be a delta PL. When we increase, there will be a reduction in the flow. Here you can see that if you increase PL, there will be a reduction in the flow QV. So if you take the small signal gain, that gain will be negative normally. So I want to make that coefficient numerically as positive, so that negative sign is taken explicitly outside. And now it is more physically meaningful. If you increase XV, QV will increase. If you increase PL, here QV will decrease. Here you can see, if you increase PL, because of this negative sign, QV will decrease. So to make that effect, influence of delta XV and delta PL more clear, that's why we had taken this as negative sign by defining Kc itself as minus partial derivative of QV with respect to PL. We get this equation and we can solve. So this is all about that explanation. Any doubts on this? Now your job is, you have to study that course note which I have given. And with this explanation, you understand it, how it works. If I think I should give a break, you have to now study. And I hope if you want any additional lecture, next Friday morning you have Qs, right?
Yes, sir.
Then if required, I can give a small introduction the next Friday afternoon prior to the lab for the course note, so that you can straight away go into the linear simulation of that. Now you have to, I am giving you a home assignment to study this well and read the course note and understand it, so that I can quickly scan through the course note and teach you. Okay.
Sir, is it already uploaded on Moodle?
Course note already you got, so Abhilash might have given you. This I am going to give you now. Today's lecture, Abhilash will give you. I am going to send him.
Yes, sir.
Other course note you received, right? Printed note. That lab hydraulic actuator theory you have received, right?
I will check, sir.
Okay. Otherwise, I will check with Abhilash. I have sent him last week itself. Okay. Okay then. All right.